Ever wondered how a tiny device makes a roaring airplane disappear? Imagine settling into your seat, the engines whine to life, a symphony of industrial clamor building around you. You press a button, slip on your headphones, and suddenly, that oppressive rumble isn't gone, exactly, but it's transformed into a distant, gentle hum, almost a whisper. The world outside, just moments ago a cacophony, now feels strangely quiet, leaving you in a bubble of serene solitude, perhaps with your favorite podcast or music playing softly. It's a sensation that feels like magic, doesn't it? Like a tiny, personal force field against the noise of modern life. But this isn't magic. It's a marvel of engineering, built upon fundamental principles of physics. Noise-canceling headphones don't just block sound. They actively create silence. They fight noise with noise, turning the very thing that assails your ears into its own undoing. Today, we're going to pull back the curtain on this incredible technology. We'll explore the ingenious science that allows your headphones to analyze the chaotic symphony of the world around you, identify its disruptive elements, and then, with breathtaking speed, generate an opposing force that quite literally cancels out the unwanted sound waves. We'll delve into the physics of sound, the clever electronics, and the real-time processing that makes this all possible. By the end of this journey, you'll not only understand how these devices work, but you'll gain a newfound appreciation for the silent revolution they've brought to our noisy lives. To truly grasp how noise-canceling headphones perform their auditory disappearing act, we first need to understand their adversary, sound itself. What is sound? At its most basic, sound is a vibration that travels through a medium, like air, water, or even solid objects. Think of it like ripples spreading across a pond when you drop a stone. The stone disturbs the water, creating a disturbance that propagates outwards. Similarly, when something vibrates, a speaker cone, a vocal cord, a jet engine, it pushes on the air molecules around it, creating regions of compression where molecules are squished together and rarefaction where they're spread apart. These regions then push on adjacent molecules, and so on, propagating the vibration as a wave. These sound waves have several key characteristics. First, there's amplitude, which we perceive as loudness or volume. A larger amplitude means a more intense vibration, a bigger ripple, and thus a louder sound. Second, we have frequency, which is the number of wave cycles that pass a point in 1 second. We perceive frequency as pitch. High-frequency waves have more cycles per second and sound high-pitched, like a flute or a child's voice. Low-frequency waves have fewer cycles per second and sound low-pitched, like a bass guitar or the rumble of an engine. The distance between two consecutive peaks or troughs of a wave is its wavelength. Higher frequencies have shorter wavelengths, while lower frequencies have longer wavelengths. This difference in wavelength is crucial because it affects how easily sound can be canceled, as we'll soon see. Finally, and perhaps most critically for noise cancellation, there's phase. Imagine two identical waves moving through the same space. If their peaks and troughs align perfectly, they are in phase. If the peak of one wave aligns with the trough of another, they are out of phase, specifically 180 degrees out of phase. This concept of phase is the secret sauce of noise cancellation, the very core principle upon which the magic is built. When sound waves combine, they undergo a phenomenon called superposition. If two waves are in phase and combine, their amplitudes add up, making the resulting sound louder. This is called constructive interference. Think of two people pushing a swing at the exact same moment. The swing goes higher. But what if those two waves are perfectly out of phase? What if the peak of one wave meets the trough of another, and they have the exact same amplitude? In this remarkable scenario, they don't add up, they cancel each other out. The positive pressure from one wave perfectly negates the negative pressure from the other, resulting in a flat line, a momentary absence of sound. This is called destructive interference. And there it is, the fundamental principle behind noise-canceling headphones. They don't just block sound. They listen to the unwanted noise, then generate an anti-noise sound wave that is precisely 180 degrees out of phase with the original. When these two waves meet, they destructively interfere, effectively canceling each other out and leaving, ideally, silence. Imagine those ripples on a pond again. You drop a stone, creating ripples. Now, If you could instantly drop a second, identical stone at the exact same spot, but perfectly timed so that its troughs align with the first stone's peaks, and its peaks with the first stone's troughs, what would happen? The water would stay perfectly still. It's an elegant solution. Fight sound with sound. The genius lies in the precision required to achieve this. So, how do headphones actually pull off this trick in real time? It's a fascinating interplay of miniature microphones, sophisticated digital signal processors, and tiny speakers, all working in a continuous, high-speed feedback loop. This is where active noise cancellation, or ANC, truly comes to life. The process begins with tiny microphones, typically located on the outside of the headphone ear cups, facing outwards, and often another set inside the ear cups, closer to your ear. These microphones are the ears of your headphones. Their job is to constantly listen to the ambient sound in your environment. They pick up the low hum of the airplane engine, the chatter of voices, the rumble of traffic, whatever noise is trying to invade your personal space. Once the microphones capture these ambient sound waves, they convert them into electrical signals. These signals are then immediately fed into the brain of the operation, a sophisticated digital signal processor, or DSP. This is where the magic really happens. The DSP is an incredibly powerful, tiny computer specifically designed to perform complex mathematical calculations on audio signals in real time. What does the DSP do? Its primary task is to analyze the incoming sound wave. It determines its amplitude, its frequency, and most critically, its phase. Once it has this information, the DSP's next, astonishing step is to create a brand new, artificial sound wave. This isn't just any sound wave. It's an inverted version of the original. It has the exact same amplitude and frequency as the unwanted noise, but it is precisely 180 degrees out of phase. If the original sound wave is at a peak, the DSP generates a trough. If the original is at a trough, the DSP generates a peak. This is the anti-noise wave. But the DSP can't just generate this anti-noise and be done with it. It has to do it incredibly fast. Sound travels at approximately 343 meters per second in air. For the anti-noise to effectively cancel the original noise, it needs to reach your ear at virtually the exact same moment as the original noise, but perfectly out of phase. This means the DSP has mere microseconds to complete its analysis, generate the anti-noise signal, and send it to the headphone speakers. This real-time processing capability is one of the most demanding aspects of ANC technology. Finally, the newly generated anti-noise signal is sent to the headphone's internal speakers, the very same speakers that play your music. These speakers then emit the anti-noise wave directly into your ear canal. When this anti-noise wave, perfectly crafted to be the inverse, meets the original ambient noise wave that has penetrated the headphone's passive barriers, they collide. And thanks to the principle of destructive interference, they cancel each other out, significantly reducing the perceived volume of the unwanted sound. This entire process is a continuous feedback loop. The microphones are always listening, the DSP is always analyzing and generating, and the speakers are always emitting. The internal microphones, closer to your ear, even monitor the residual sound after cancellation, feeding that information back to the DSP to refine its anti-noise generation and ensure the most effective cancellation possible. It's important to note that ANC is particularly effective at canceling out low-frequency, continuous sounds. Think engine hums, fan noises, the drone of traffic. These sounds have longer wavelengths and are more predictable, making them easier for the DSP to analyze and counter. High-frequency sounds, like speech, sudden sharp noises, or irregularly changing sounds, are much harder to cancel effectively. They have shorter wavelengths and more complex, rapidly changing characteristics, making it incredibly difficult for the DSP to generate an accurate, perfectly out-of-phase anti-noise wave in time. This is why even the best noise-canceling headphones won't completely silence a conversation happening right next to you, but they can make that jet engine virtually disappear. Now, it's crucial to understand that active noise cancellation doesn't work in isolation. Most modern noise-canceling headphones employ a dual strategy, combining ANC with what's known as passive noise cancellation, or PNC. Passive noise cancellation is the simpler, more intuitive approach. It's essentially about physically blocking sound waves from reaching your ears. Think of wearing earplugs, or even just cupping your hands over your ears. The effectiveness of PNC depends on several factors. The materials used in the headphone ear cups, dense foams, thick plastics, the design of the ear cups, how well they seal around your ears, and the overall fit. Over-ear headphones, for instance, generally offer better passive noise isolation than on-ear headphones because they enclose the entire ear, creating a better seal. Similarly, in-ear monitors with well-fitting ear tips can offer excellent passive isolation by essentially plugging your ear canal. PNC is good at blocking a wide range of frequencies, especially higher ones. The denser the material and the tighter the seal, the more sound energy is absorbed or reflected before it can reach your eardrum. However, PNC has its limitations. It's hard for passive methods alone to effectively block very low-frequency sounds, like the deep rumble of an airplane engine. These long-wavelength sounds can more easily penetrate physical barriers. To achieve significant passive noise reduction, headphones would need to be incredibly bulky, heavy, and potentially uncomfortable. This is where the beauty of a hybrid system comes in. Modern noise-canceling headphones leverage both active and passive techniques. The physical design of the headphone provides a first line of defense, passively blocking a portion of the ambient noise. This passive barrier is particularly effective against higher frequency sounds and impulsive noises. Then, the active noise cancellation system steps in to tackle the remaining, typically lower frequency, persistent noises that passive methods struggle with. Many high-end headphones employ an advanced hybrid ANC system. This means they often have multiple microphones, feed-forward microphones on the outside of the ear cup, which capture ambient noise before it even reaches your ear, and feedback microphones on the inside of the ear cup, which listen to the sound that actually makes it past the passive barrier and the initial cancellation. The feed-forward mics give the DSP an early warning, allowing it to generate the anti-noise proactively. The feedback mics then act as a quality control, monitoring the residual noise right at your eardrum and allowing the DSP to fine-tune its cancellation in real time, creating a more precise and effective silencing effect. This combination of external and internal microphones, along with the physical design, allows for a much broader and more effective range of noise reduction. So, when you put on those premium noise-canceling headphones, you're not just relying on one technology, but a sophisticated partnership. The physical barriers of passive cancellation working hand-in-hand with the dynamic, intelligent anti-noise generation of active cancellation. Together, they create that remarkable bubble of quiet that feels so isolating and empowering. While noise-canceling headphones are undeniably impressive, they aren't without their challenges and limitations. Understanding these helps us appreciate the complexity of the technology even more and also manage our expectations. One of the biggest hurdles for ANC is latency. As we discussed, the DSP needs to analyze the incoming sound, generate an inverse wave, and output it through the speakers, all within milliseconds. If there's too much delay, even a tiny fraction of a second, the anti-noise wave won't perfectly align with the original noise wave. Instead of perfect destructive interference, you might get partial cancellation, or even worse, constructive interference in some frequencies, making certain sounds louder. This latency is a primary reason why higher frequency sounds are so much harder to cancel effectively. Their wavelengths are shorter, meaning their peaks and troughs occur more rapidly. A tiny delay can cause a significant misalignment in phase, making accurate cancellation extremely difficult for rapid, complex sounds like human speech. Another critical factor is the fit of the headphones. For both passive and active noise cancellation to work optimally, a good seal around your ears is essential. Any gaps can allow sound to leak in, bypassing both the physical barrier and the active cancellation field. This is why manufacturers invest heavily in ergonomic designs, comfortable earpads, and adjustable headbands. Even slight variations in how you wear your headphones can impact their performance. The type of noise also plays a huge role. ANC excels at steady-state, low-frequency noises. Think engine hums, air conditioning units, or the constant drone of highway traffic. These sounds are relatively predictable, making it easier for the DSP to identify their characteristics and generate a consistent anti-noise signal. Conversely, sudden, sharp, or intermittent noises like a car horn, a slamming door, or people talking loudly are much harder to cancel. Their unpredictable nature and rapid changes in frequency and amplitude mean the DSP has less time to react and generate an accurate inverse wave. This is also why speech, with its complex combination of frequencies and constantly changing patterns, is challenging for ANC to fully eliminate. Power consumption is another practical consideration. All that real-time processing and signal generation requires energy, meaning ANC headphones typically rely on rechargeable batteries and have a finite operational time for the noise-canceling feature. The more sophisticated the ANC, the more power it generally consumes. Despite these limitations, the technology is constantly evolving. Future advancements are likely to focus on even faster and more powerful DSPs, allowing for better cancellation of a wider range of frequencies and more complex sounds. We might see the integration of artificial intelligence and machine learning, enabling headphones to learn and adapt to specific environments or even specific types of noise, personalizing the cancellation experience. Imagine headphones that could selectively cancel out a specific person's voice while allowing others through, or create a customizable soundscape based on your preferences. We're also seeing improvements in microphone technology and transducer design, allowing for more accurate sound capture and anti-noise emission. The quest for smaller, lighter, and more energy-efficient components continues, promising even more portable and long-lasting noise-canceling devices. The future of quiet is exciting, offering the promise of even more immersive and personalized auditory experiences. So, let's quickly recap the incredible journey we've taken today. We started by understanding sound as a wave, characterized by its amplitude, frequency, and crucial for our discussion, its phase. We then discovered the ingenious principle of destructive interference, where two waves perfectly out of phase cancel each other out, creating silence. This is the core magic behind noise cancellation. We saw how active noise cancellation headphones bring this principle to life. Tiny microphones listen to the ambient world, feeding those sound waves to a super-fast digital signal processor. This brain of the operation instantly analyzes the incoming noise and, with breathtaking speed, generates an identical anti-noise wave that is precisely 180 degrees out of phase. This anti-noise is then emitted by the headphone speakers, meeting the original unwanted sound waves and causing them to cancel each other out right before they reach your eardrum. We also learned about the vital partnership between active and passive noise cancellation, explaining why modern headphones combine physical sound blocking with electronic sound cancellation for the most effective results, especially against those persistent, low-frequency hums. And finally, we touched on the challenges like latency, fit, and the complexity of different noise types, as well as the exciting future possibilities for this ever-advancing technology. From the roar of a jet engine to the peaceful hum of your own personal space, noise-canceling headphones are a testament to human ingenuity, transforming chaotic vibrations into a profound sense of calm. The next time you put on your headphones and the world around you quiets down, you'll know it's not magic, but the elegant dance of waves, meticulously orchestrated by a tiny, powerful computer. If you found this explanation as fascinating as we do, please consider giving this video a like and subscribing to our channel. We love bringing you these deep dives into the science that shapes our world. And let us know in the comments below, what's the nosiest place you've brought your noise-canceling headphones, and what was your experience like? We'd love to hear your stories. Until next time, stay curious and keep listening to the wonders of science.